Alright, so in continuation with the previous class, we can see that we had this voltage source and a simple resistor based network in which we perform operating point analysis. So what we did is that we chose the edit simulation command. We saw that we had chosen DC operating point, and this particular analysis or spice command gave us the various voltages and currents that are operative in this circuit. Okay, and now the next analysis we can do is that DC transfer. So direct current transfer analysis helps to find the DC small signal transfer function. We'll understand in deeper sense what is small signal transfer function when we'll move to the AC analysis. Right now we'll just focus on how to find the DC transfer function. So it needs to provide two parameters. One is the output and one is the source. So input source, output is at what point, at what node in the circuit we are interested, that is output. So for example, in this particular resistive divider circuit, we are interested at this node. Well, at this net, we have labeled this net as a VO. So we can write that we are interested in to see the output at this net. So V in parenthesis will write VO. So V of VO is the output. And what is the source? Source could be a current source or a voltage source. In our circuit we have a DC voltage source whose name has is V1, so we'll just write V1. So we can be okay with the small case letter or the large capital letter, so it is fine. So as soon as we type over these two, we provide the names of the output and the source, we see that the syntax is created here. So that spice command is .tf. tf stands for transfer function V of VO and space V1. So it provides us the transfer function between output and input of this particular circuit. So we'll see more on that. So then we can click, and the spice command is available. We can place somewhere here on the circuit. So what is it going to give is the transfer function is the ratio of output over input basically. There is a Laplace involved also. If we have capacitances and inductances into the circuit, we'll see that how the transfer function evaluated, in which case the transfer function will be the ratio of Laplace of output to the Laplace of input. So we'll see that later. So right now we do have only a resistive network. Connected across this resistive network is a voltage source whose value is 1 volt. We can provide the value as from the previous lecture. We see that. So, and series resistance, we can provide some value, or we can just keep it right here. If we click on advanced, what we see is we have selected none, which is a DC voltage source, which indicates a DC value. We have given it before. We can write it here 1 volt, and we are not interested in filling other details of this one, so we'll just click OK. So that is how it goes. So in the previous video we have run the operating point analysis, which provided all the voltages and the currents into the circuit. The command for that was .op, the spice command. Now in this particular lecture we are interested in performing the transfer function analysis, in which the command is .tf. Okay, and that is a syntax .tf, V of VO and V1. and the circuit remains same. The resistors R1 and R2, they are in series, both have the values of 1 kilo ohm. And now this is the way, one way on the screen of this circuit simulating software we can draw the schematic. In another way, what we can do is that we can go to edit, and we can see that how the netlist is created. So for example, we can go to view, and there is one function over here, spice netlist. So if you want to create a circuit, design a circuit and simulate it, so one way is to use the circuit simulating software such as what is being shown. Draw the schematic by choosing the components and devices from the library. And another way is to create a blank text or document such as MS Word, or we can also use the text pad, notepad, and on that blank page we can create or type the spice netlist such as this. So now this, because we have already designed, drawn the schematic on the screen, so this program, spice program, has already created automatically the netlist for us. So what we can understand from this netlist is, look at that, the resistor R1, the first line, that says it is connected between two nets. The name of the two nets is NOO1 and VO. So we can also see that this resistor R1 is connected between net, the one terminal of it is connected to this net. So this net is, spice has named it as NOO1, and another terminal to which R1 is connected, we have named it as VO. As we can see, refer from the last lecture, we have named this net as a VO. So, and it has a value of 1K, resistor has a value of 1K. TOL is the tolerance, as we've seen in the previous class, is a 1%. PWR is the power rating. So these two can also be skipped if we are not interested in, we don't need to write it exclusively. So now R2 is connected between net VO and the ground, which is VO and 0. It has a value of 1K. The source V1 is connected between NOO1 and ground, right here between the two terminals. It has a value of 1 volt. Now the components and the sources has been described. We can write it in the separate blank text notepad or something like that, and then run the simulation. Now which simulation we are interested in, that is given by the spice command. So we have also given in the schematic by the menu, or we can write it as a .tf, v of VO and V1. So we are interested between the transfer function at the output node and at the input node. Okay, and this back annotation .back annotation, we can always see from the help menu what this command refers to. And finally, most importantly, you have to end the spice netlist by specifying .end command. What if we want to label the net, as we have seen that, let us say we go back right here, right click on this net and click label net, and we type V in over here, and this is the input net, so we select input, okay, and then we just press Ctrl R from the computer keyboard, and so that we can actually try to rotate it. Okay, for example, we can just label it and we in input, and we try to place over here, escape, try to connect it. Okay, so that is how it is done. And now if we say when we want to see it, now the new spice netlist, and we see that now this resistor R1 is connected between V in and VO, unlike the previous netlist. Now we have the voltage source V in V1, which is connected between two nets V in and O. So if we are interested in specifying and labeling each and every net in the network, the SPICE netlist gets modified as this. So having done that, we are all set to run the simulation, and what we are interested in here is to see that what is going to be the transfer function, which is the ratio of output over input. So we can also, because this is a simple network, we can also tell what is the ratio of output over input. So it is basically R2 divided by R1 plus R2, which is the output, multiplied by V1. So VO will be R2 divided by R1 plus R2 into V1. So that is your output expression, and the ratio of VO over V1 will be simply R2 divided by R1 plus R2. So because this is a simple network, we can also tell it by inspection. So that is a one task or one benefit of performing this transfer function analysis. There is another function of this analysis is to tell what is the input impedance of this network, and also what is the output impedance of this network at a particular node. So input impedance of this network is simply, we just take out this voltage source and we can see that what is left in the network, which is simply two resistors which are connected in series. So input impedance would be a sum of these two resistors, which is 1k plus 1k, which is 2000 ohm, and the output impedance or output resistance at this node, that is at VO, will be determined by what is the calculation we can do over here. Okay, yeah, so output impedance will be calculated as SPICE will short circuit this voltage source over here. With that action, R1 will come in parallel with R2, so the equivalent output impedance will be a parallel combination of these two resistors, which is 0.5 kilo ohm or 500 ohm. So transfer function will provide the ratio of output over input impedance of this network and the output impedance of this network at a particular output node. So these are the three advantages of doing a transfer function analysis. So now let us run this simulation and see how the analysis results are. So we run this, and what we can see over here, first output line is a transfer function which is 0.5, as we can also see by inspection. It is the ratio of output over input, and input impedance, which is seen by this voltage source V1, which is 2000 ohm, as we calculated also by inspection earlier, and the output impedance at the node VO, which is right over here, that we also calculated, which is 500. So this is how SPICE can give the output by performing some simulation. If the circuit complexity becomes higher, at that time SPICE comes handy to do these automatic calculations and to accurately predict the circuit response to a given stimulus. Okay, so with that said and done, let us do some changes and rerun the analysis again to see what happens with this new set of changes. So instead of this voltage source, now I am interested in putting a current source over. So I will just try to find the current source. I just type CU, and the current source is available over here. As we can see that it could be a DC current source, AC, pulse, sine wave, etc. So I will click over here and I will press Ctrl R from the keyboard to change the direction of this current source, and we'll connect over here. And then now I have this current source. I will right click over here and I will try to input the value. So I am interested in input value of 1 ampere. I can click on advanced, so you can see there I have seen none. I have selected none, so it is a DC current source. Its value is 1 ampere. I have already provided, so no need to again write it in this space. I will click OK, and the other network remains same. I would like to change the name of this net, since it is now a current source. What I'll do, instead of V in, I will write I in, and that's how I go it. How about the transfer functions? Again, now I am interested in the transfer function, which is the ratio of output by input. So VO is my output, which is the output voltage at this node, and I in is the input source, which is the input current source. Okay, so in that situation I will right click on this command. As we can see that I will just take the mouse cursor over here, right click, this window will pop up, and output and the source I need to define to compute the DC transfer function of this specific network. So what I'm gonna do is, output is going to be the same, which is V of VO, and the source will get changed. So instead of voltage source V1 earlier, I now have a current source I1 over here. So once I change that, the syntax for the command gets changed automatically, and I will just click OK. Now I am interested in seeing, if I am interested in seeing how the netlist is modified, I can again go to view and click on spice netlist over here, and we can see that R1 and R2, there is a current source connected between 0 and I1. Now one thing to note over here, the direction of these current source is important based on the what is going to be the current and what is going to be the direction. Okay, so I in is connected between 0 and I in, so it's from ground to this, that's why the arrow is upward. If I change the direction of this current source by Ctrl R in the as shown before, so if the this arrow is downwards, so it means the current is flowing in this direction, and this netlist will get modified such as I in and 0. Okay, so and then there comes the transfer function command .tf as before, and final command is .end. Okay, so now we are interested in what is going to be the output divided by input, what is going to be the input impedance of this network, and what is going to be the output impedance of this network. So before running the transfer function analysis for the same network, we can also run the operating point analysis. So instead of before running the transfer function analysis, let's say I want to compute all the currents and the associated voltages of this particular network, so that I can do. So I1 I haven't defined, so how I can do, let's define the value of I1 first. It is 1 ampere, and I will just click OK, so that the current source has a value of 1 ampere. Registers are 1k each, and now I am interested in running the operating point analysis first. So DC operating point, I'm gonna click. This is going to create a syntax for me, and now I am seeing that automatically it creates a command, and I am going to, not really, this is not the way we can do it. What we just do is just cancel this out and run the simulation again, edit the simulation again. So go to simulation command, click DC operating, and we have only this command .op. So we just place it over here. So once that is done, it will compute all the operating points. So what we can see is that, let's say I'm interested in knowing what is the output voltage for this given source of 1 ampere current source and the resistor. So the current is going to flow in this direction, and that's going to flow through R1 and R2. The current is same, and current through R1 is 1 ampere, current through R2 is 1 ampere, and the voltage across the output, voltage across the resistance R2 is nothing but VO, which equals to R2 multiplied by the current flowing through it, which is 1 ampere. So the VO will be 1000 volt, 1K into 1 ampere. Alright, similarly, if I am interested in the equivalent resistance of this network, I can see that equivalent resistance, they are two in series, so that is the 2000 ohm. Let us now run the analysis and see what all parameters it gives me. So I've run the simulation, and what we can see is that the voltage at the node or at the net I in at this particular point, what is the voltage? So it's basically, it's giving me 2000 volt. How it's going to give me 2000 volt, and we have to understand that. Similarly, what is going to be the voltage at the VO? So 1 ampere is flowing over here, so 1 ampere into 1K, so that is the 1000 volt over here, and 1 ampere is also flowing through the resistor R1, so which is 1000 volt over here across this resistor. So 1000 volt and 1000 volt with respect to ground, at this node I in, we have a voltage of 2000 volt, so that's correct. Now I of I1, which is the current from this current source, which is 1 ampere. The current through R2 is 1 ampere, current through R1 is 1 ampere. So that is how the SPICE provides the operating point analysis, and it gives information about all the voltages and the currents of the particular network. Having done that, we can now cancel this analysis. We go back again to the simulation command, and instead of DC operating point, now we will perform the DC transfer function analysis. So now again, what we are interested is computing the output voltage, which is V of VO. I'll just type here, and the source is the DC current source, the name of which is I1, and the command is available here. And now I'm going to place this command over here, and before running the simulation, I would like to theoretically investigate, because this is a simple network, I would like to theoretically investigate what is the output voltage, what is the input impedance, and what is the output impedance. So the input, what is the output? VO, and the input is I1. So I1 is flowing through R1 and R2. Okay, so VO divided by I1 is basically the resistance. So the transfer function is a resistive over here. So 1000 will be the transfer function. Okay, and we have this input impedance again. What is the input impedance? Is basically the summation of these two resistances, which is 1K and 1K. and the output resistance will be the resistance seen from this particular node inside the circuit. So it is basically the V output divided by the current flowing through this resistor, which is 1 ampere. Okay, so we can see that how it computes. So as we can see that transfer function is 1000, which is the ratio of VO divided by 1 ampere. So again, V output we can compute how 1 ampere flows through resistor R2. Okay, so V by I is nothing but the resistance, that is 1000 ohm. Input impedance seen by this current source is 2000, because the summation of these two, because this current source will get open circuited by the spice. That's how it is the summation of these two resistor. Output impedance at this node VO is again 1000. Okay, so output impedance is basically the voltage divided by current. So voltage is 1000 volt, current is 1 ampere, so 1000 divided by 1 ampere is 1000 ohm. Okay, so that is how it goes. It provides us the complete analysis. So this is how we can do the operating point analysis and the transfer function analysis for a given network. In this lecture we've seen that how to create netlist, how to draw the schematic, how to run the simulation, how to perform different analysis, how to theoretically investigate a specific circuit. It will always be advisable to do some hand calculations on with the paper and a pen before running the simulations, and once that is done we can always cross check our hand calculation with the simulated results, as we've done over here, as we've shown through the simulations. Because the circuit was very simple, we could by inspection, visual inspection, we could compute and calculate all voltages and currents existing in the network. However, and then we could compare it with the simulated results by the spice. However, if the circuit complexity goes higher, it is very imperative to first do hand calculations and do the detailed analysis, and then we can run the simulations. And if there is an error, it's always nice to go back to circuit analysis and cross check the analysis. So that's all for now. We'll continue with the next class.